Alright, hey guys, how's it going? So, Professor DePaolo here. We're going to cover Chapter 6 today. And this is kind of weird because it's my first lecture ever on like a podcast kind of setup, but let's do our best. So, just to give you an idea of what's going to happen for the rest of the class, we're going to do these online lectures, and I'll post them to Blackboard every week. And our assignments will be due in Blackboard. So, I'll show you that right now. So, I'll go to Blackboard. So, here's the Friday class. Is the announcement. So what's going to happen is every video will be located under course materials. And I didn't put them here yet, but it'll go under a new folder called lecture videos. And I'll put chapter 6 and then so forth. And I might even go back if I have enough time to put in chapter 2 through 5, just so we have a full lecture library so you can go through it when you study. All right. So under assignments is where we're going to see all of our assignments. And same thing as we've always done, where it's going to be under homework. And for Chapter 6, here's Chapter 6 homework file submission. So you will click that and you'll upload your file. I have the teacher's version, but you see right here, you can attach your file. And here's the files in PDF and doc. And you can do them on your computer and then upload the finished product up to your files. And I'll keep reminding you on the announcements to tell you when everything is due. So don't worry about that. Also, I'm implementing discussion boards. So I didn't start one yet, but I will create forum under discussion board under that tab on Blackboard, and I will put Chapter 6 discussion board, Chapter 7, Chapter 8, etc., just so you have an outlet to ask any questions if you have any. And I will answer them in real time, probably within the hour, because I have nothing else to do, right? Okay, so with that being said, let's get started. Chapter 6. I'm sure you don't want to be listening to me for too long. So this lecture is going to be faster than the in-class lectures because there's no questions and I don't have to repeat myself many times. So what you can do is if you don't understand a concept, which granted, this chapter is pretty difficult, you can go back and rewind it as much as you want. And I think you could even slow it down depending on what media viewing software you're using. So, all right, let's get into it. So, hold on, move this out of the way. All right, so Chapter 6. So in Chapter 6, we're learning about the types of bonds, right? And you have ionic bonds and covalent bonds, so the main two types of bonds. And up until this point, we've been learning about the individual atoms, the nucleus, which is the protons and neutrons, and then the electrons go around it. Today, we're going to be learning more about the electrons, what happens if you change the number of electrons. And we've been assuming that a lot of these atoms, really all of them, are considered neutral. I know I said that during class a lot. We consider them neutral, meaning their protons and their electrons are the same number. And this case, in Chapter 6, we're diverging from that old philosophy, and we are changing the number of electrons, and we're seeing what that does to different types of bonds. So we're first going to go over ionic bonds and how to name every single ionic bond. Then we'll do covalent bonds, and we'll learn how to name those. So the naming, I have some really important slides in here. I think it's slide number 97 that really sums up the rules for different, how to name every type of compound, really, that we're going to encounter. So definitely look at that, but we'll go through it right now. So every chemical bond likes to, or to make these chemical bonds, we want to gain, lose, or share valence electrons. So these valence electrons are on the outer side. I want to see if I can do this. Hold on. Highlight cursor. Hold on. Highlight clicks. No. All right, I'll work with the effects later, but and I want your feedback from this lecture because if you can't hear me too well or there's another problem, I'll fix that. Anyway, so they like to, in ionic and covalent bonds, like to exhibit this octet rule, meaning octet meaning 8, oct, right? It's octagon. So basically, the electrons like to be happy. And what that means is they like to have an outer valence shell of 8 valence electrons, whether it's ionic bonds or covalent bonds. So just keep that in mind for right now. It's not really going to come into play right this minute, but when we learn about ionic and covalent specifically, you'll see how this takes effect. All right, so the first type of bond is ionic bond. And it occurs when valence electrons of a metal are transferred to the nonmetal, right? So you have this transfer of electrons. That's a key thing. So if you imagine that you have a a neutrally charged, let's say sodium, right? Sodium, if you look in the periodic table, has one valence electron. And when you lose that valence electron, it's originally neutral. If you lose an electron, you're losing a negative. If you lose a negative, your element's becoming positive, right? So that's exactly what's happening. When the ionic bond metal loses an electron, either one or more, it gains a positive charge. And that electron or electrons that it gives to the nonmetal makes the nonmetal have a negative charge. And that charge difference, the plus and minus, that's created from the transfer is what brings them together like magnets, like a plus and minus. But it's electrostatic. It's a little bit different than that. Okay. I'm going to turn the volume up a little bit. All right. So then we have covalent bonds. And covalent bonds are between non-metal atoms, right? One or more. And they share valence electrons to obtain this noble gas arrangement. In other words, obtain the octet. Because you notice that if you look at the periodic table, all noble gases have 8 valence electrons. So, except for helium, which has 2, because it can only fit 2 because it's very small. But the other ones, they do. Okay, so let's continue. Can I click? There we go. All right, so here's a perfect representation of what I was just talking about. So the transfer of electrons from the metal, this is M stands for metal, not for a specific element, and NM is for nonmetal. So let's say this is a sodium, which has 1 valence electron. It gets transferred over to the nonmetal because the nonmetal is very close to 8. Remember this octet rule, we always want 8 valence electrons. Now, the closer you are to 8 as an element, for example, the halogens, they all have 7. If you have 7, you only want 1 more. That means you're going to really want that 1 more. You're so close to the finish line of having 7 or having 8 that you'll basically react with a lot of things in order to get that 1. And on the contrary, if you're a metal that has maybe 1 or 2 valence electrons, in this case 1, you want to lose that electron because you're closer to 0. And really, if you lose this 1, you have 0. But in actuality, there's also layers of electrons underneath this. This depiction is only showing the valence electrons. There are other already completed shells, like we learned about in chapter 4. There's other completed shells underneath the valence shell, and those already have 8. So for metals, they want to lose 1 or more electrons. Non-metals, they want to gain 1 or more electrons. That's the basic idea. And once they do that, they get the charge, a plus and a minus, and it brings them together. Covalent, they work in the same way, but they're kind of smart about it. So if you look at the same nonmetal over from the ionic case, comes over and it sees another nonmetal. Oh, I want 1. This one wants 1. Hopefully you can see my cursor. 1 valence electron, right? The other nonmetal, there's no other metals to take it from. So the other nonmetal that it goes near will be like, hey man, I want 1 valence electron. The other one's like, oh, I need 1 also. What do? They don't transfer 1 from the other. That wouldn't really do anything. That would just switch electrons. What they do is they share the electrons. And once they share, those shared electrons are considered to be part of both valence shells. So they actually have overlapping valence orbitals. And you can see that if you count the kind of like a Venn diagram thing, if you count everything in this first nonmetal, you see that it has 8. 1, 2, 3, 4, 5, 6, 7, 8. The other one has 8 as well. That means it's happy. So that's all good. All right. So who cares about this? This is just basically what I said. All right, don't worry about it. All right, same thing like I just said. We're talking about, in this case, we're talking about specific cases. You have sodium, then it loses the electron, becomes sodium with 1 less electron. Duh, right? Obvious. So we'll skip this for now. Same thing for magnesium, but magnesium has 2 electrons. And when it loses its 2 electrons, it has a 2+ charge, meaning the difference in charge, the difference in protons and electrons is 2 more weighted on the proton side. You see our protons positive are 12, electrons negative are 10. So the difference in that is 2, so the charge would be 2. So basically what happens, the number of valence electrons a metal has, it loses them, and it becomes that charge, plus. So magnesium has 2 valence electrons, loses them both, 2+. Aluminum has 3, loses all 3, 3+. Iron could have 2 or 3, loses either 2, becomes 2+. When it loses 3, 3 plus. Very simple. Okay, so now we're going to learn about the same thing for the nonmetals, really, but the nonmetals are doing the opposite. They are gaining the electrons that the metals will lose. So chlorine, in this case, it has 7, because it's in 7A. It gains 1 more, becomes 18 total, and it has 17 protons. The difference is 1 towards the electrons, meaning it's 1 more than the protons, so that the charge will be -1. So that's the way it works. And here's an idea of charges. Now, the charges that I want you guys to know for the test. Now, the test will also be put on Blackboard, and they'll be on assignments, but we'll talk about that after we do Chapter 7. So these are the charges that we need to know, but I have a better depiction right here. All right, so you can put this in your notes. So know the charges for 1A, right? These metals, they have 1 valence electron, all +1. 2A, 2 valence electrons, all +2. The middle here, these are transition metals. They have they only have zinc and silver and cadmium, but no one cares about cadmium. Zinc and silver are the main ones that only have 1 charge, but the other ones, since they're not even, they have so many charges that they're not even shown here. They have 2, 3, or even 4 charges, right? So don't need to know those. For naming, I say for the future, you can put in your memory that zinc is +2 always, and silver is +1, and cadmium is +2. But I'm not going to test you on that. That's just for Chem 2, that might come in handy to know. Okay, so for 3A, just aluminum, because we know that aluminum is the only metal here that is going to be not really a transition metal. They just didn't know where else to put it. Everything else here is a transition metal in 3A. And then here's boron, which is a metalloid. Then going from the other side, the nonmetals. You have 7A, which is -1, 6A, which is -2, 5A, -3. So these ones that are highlighted here, and you can see the symbol for them, I would say know those rows. And then 8A, they're noble gases. They don't have a charge. So make sure you know that. Okay, so write the formula and symbol for an ion with 16 protons and 18 electrons. Basically, the proton number, you can pause it if you want to do it on your own, but you can resume right now. And the protons tell you the atomic number, right? So it's 16. 16 atomic number is sulfur. Then it has 2 more electrons, meaning sulfur 2-. So that's how you do that. Okay, now we're going to learn about writing the formulas and the names. So sodium chloride is the way. I'm sorry if I'm going too fast, but you can pause it and slow it down. Sodium and chlorine, right? Sodium chloride, which is right here, we know it as normal table salt. There's a reason why it's called sodium chloride instead of sodium chlorine, right? Because chlorine is the element, but it goes to chloride. And that's exactly one of the key rules of naming, that you change the ending of the second element to IDE. And that's the case for ionic and covalent. But first, we're going to learn about ionic. So we talked about this already, talked about this already, but you can pause if you want to take a look at it. There's that one, this one, this one. All right. So before that, let's do a little practice. So write the ionic formula composed of Ba2+ and chlorine 1-. Now, another important concept is that since barium is 2+, chlorine is 1-, the thing you want to ask yourself is how many -1 chlorines can go into, or cancel out with, are needed to cancel out with 1 barium 2+. And you can do the math for that and see barium is 2+, chlorine is 1-. 2 chlorines will cancel out that barium and make it 0, because the net ionic charge of all ionic bonds is 0, meaning the positives cancel out the negatives. Very, very important. So you get BaCl2, like that. Okay, so we could do the same for all of these, and you can pause it right now if you want to try it on your own. I suggest do that. All right, we're back. Then you can, we just do the answers. Yep, and you can see that for yourself. If you have any questions, you could ask on the discussion board, the forum. Okay, moving on. So now we're naming. All right, so here's the rules for naming ionic compounds. Now, you can take notes on them, but I'll just tell you them right now. First is name of the metal. Always think of sodium chloride as your example. So the metal is called sodium. You just write the name of the metal. So that's it here. Write the name of the metal, written first. Same as the name of the element. Then the first syllable of the nonmetal followed by IDE. Chlorine turns to chloride. Bromine turns to bromide. And it doesn't really get much more complicated than that. Oxygen is not oxide, it's just oxide, and that flows off the tongue better, right? Nitrogen is nitride. Phosphorus is phosphide. Sulfur is not sulfuride, it's sulfide. So if you ever encounter a weird spelling thing, just say them in your head and think about which one sounds better. Whichever one sounds better is usually correct. That's how this stuff works. All right. So here's some examples. Ki, you name the metal, potassium. Name the nonmetal with the IDE ending. Iodine becomes iodide. Potassium iodide. Magnesium is here, MgBr2. Bromine becomes bromide, magnesium bromide. Al2O3, and you notice here, I mean in these two cases, we have not prefixes, we have no prefixes. We have subscripts, right? Multiple bromines, multiple aluminums, multiple oxygens. But we do not put the prefixes in ionic bonds. Very important. Do not write this down right now. Do not write prefixes when naming ionic compounds. Meaning prefixes, I mean carbon dioxide, right? That's not ionic. That's covalent. And we'll learn about the prefixes when we get there. All right. So aluminum, you just name the aluminum. And then oxygen becomes oxide, and it's simply aluminum oxide. And the reason why you do that is because there is only one aluminum oxide. You can't write ALO. That's not a thing. ALO2, that's not a thing. The only aluminum oxide is Al2O3 because the ionic charges cancel out in only this arrangement, meaning 2 aluminums and 3 oxygens. You have 3 of these negative 2s. That 3 times negative 2 is negative 6. You have 2 of these aluminums. 2 times 3 plus is plus 6. The plus 6 from the positive aluminum cancels out the negative 2 from the 3 negative 2s from the oxygen. And that's the only possible aluminum oxide. And MgBr2 is the only possible magnesium bromide. So there's no other simplified way of them to cancel out. Okay, another thing that I forgot to mention, I don't think the slides even say it, but I mentioned it to my Tuesday class already, that the positive charged entities are called cations. And I will write that right here, if I can do that. Or if you can see my screen, I'll just write it in notes. So cation equals positive charge. And then anion equals negative charge. So wherever you see oxygen, it's usually a anion if it's charged. Anything positive, all the metals, when they partake in ionic bonds, they're going to be cations. The way I think about it, cats, I like cats, right? So cats are positive. Anions, think anti, or maybe if you don't like your aunt or something, I don't know, make it negative. So bad, negative. Okay, moving forward. All right, so you can name this one. Let's name K2O, right? So you can pause right here if you want to do it on your own. And then we will start right now. So you name it. Oh, shit, where'd it go? There it is. So K2O is potassium oxide, right? Because you just name the metal. Even though there's a 2 here, it doesn't matter. You name the metal. Then you name the anion, which is the nonmetal, with the IDE ending. So oxide. That's what we do for that. Okay, next, you can name these on your own. I won't go over them here, but the same rules apply. So you can pause it, and then we'll start right now. So you can see that, and then there are the answers. Oh, there are the answers right there. Okay, cool. All right, so now, the reason why those were so easy is because we know the charges of every cation and anion that's involved. So if we go back, CaO, right? Calcium oxide. We know calcium is 2+ from looking at the periodic table. We know that oxygen is 2- from looking at the periodic table. Same applies for aluminum, magnesium, calcium, and so forth. But if you deal with transition metals, they could have multiple charge states. And here's an example. So here, transition metals, except for zinc, cadmium, and silver, like we mentioned before, that we don't need to know right now, they form 2 or more positive cations, meaning that you have to specify in a certain way which cation you're talking about, either the +1 or +2 variant, or +2 or +3, whatever. And here's how you do that. You use Roman numerals that are equal to the ion charge. So it's very important to know this, to write this down, that the Roman numeral tells you the charge of each metal atom. Charge of each metal atom. That's super important because I see it all the time where somebody writes Cu2 on the bottom, like the 2 is right here, and that means, and they think it's, oh, copper 2. No. If each atom charge is 2+, then it's 2+. It doesn't matter how many of them there are. So I'll give you examples of that. And here's some examples of metal ions, of transition metal ions. So how copper can take 2 states, +1 or +2, for example. And then you see copper 1, copper 2. Iron is iron 2, iron 3. Lead can only be in 2 and 4. I don't know why not 3, but probably energetically favorable or whatever. I always say that. It's probably the answer. Lead 2, lead 4. Chromium 2, chromium 3. So that's how it goes. All right, let's do, and here's this list again. I'll stress again. No 1A, 2A. Beryllium is weird, so don't worry about beryllium. 1A, 2A, don't worry about the middle. They're transitions. 3A aluminum, and then 7A, 6A, 5A. And that's it. All right, so let's do FeCl2. So you can try this on your own. You can pause it, but we'll just keep going. Okay, so the idea for these, we do not know the charge of iron. Well, the answer is right here. But originally, we don't know the charge of iron. The way to figure it out is to see the anion and see what we do know the charge of. In other words, we know the charge of chlorine. We know that every time we see a chlorine anion, it's -1. There are 2 of them here, meaning -2. To oppose -2, you need +2. Therefore, the iron atom right here, there's only one of them. Iron atom is +2. Iron 2 chloride. That's basically it. Let's do another one. All right. SNO2. So you can pause it right now if you want to do it on your own. Okay, but we'll just keep going. All right. So same thing applies. We know oxygen. Oxygen is 2-. So 2- times 2 of them, 4-. Then what opposes 4-? 4+. Tin 4. That's it. So tin 4 oxide. SN is tin, by the way. Probably some Latin reason. I don't know why. Okay. So here are some other examples of ionic bonds using transition metals. So you can see a bunch. Okay. So now we will do the opposite way. We will go from the name to the formula. So iron 3 chloride, right? You know iron already. You know it's +3. So you write, because it tells you iron 3. So you write iron, you write Fe plus 3+. Then you can write chlorine. You know what chloride is. Chloride is always -1. How many chlorides need to cancel out the Fe3+? And the answer is 3. So we can just do the math right here. Fe3+ is just one of them, right? So 1 times 3+ is +3. And then there has to be 3 Cl- for them to cancel out to -3, and the +3 cancel to 0. Okay, next time on this, I feel bad now. Next time I'm going to have like a writing pad. I'll try to get it hooked up on the screen so you can see everything and see me writing things. So, because I feel at a disadvantage. But I really strongly recommend you guys send me feedback and ways to improve, things that you would like to see on these lectures, because I'm new to doing it online like this. Makes me want to do podcasts eventually, like chemistry podcasts, but with my stupid jokes. Who knows? Okay, so you can try these on your own. You can pause it, and then now I'll just talk about it. So for nickel 2 sulfide, right? We know sulfur. We know both of them. The name tells you the charge of everything, because nickel is 2+. Boom, 2+. Sulfur, if you look at periodic table, always 2-. NiS, 1 and 1 cancel out. zinc chloride. Now, zinc is one of those ones that, yes, is in the transition metal category, but it only has one charge, which is +2. So you do not have to use a Roman numeral for zinc. But again, I will not test you on the 3 exceptions, those being zinc being +2, silver being +1, cadmium being +1, right? See, even I don't know. Let me double check. I want to get this right. Cadmium is +2, right? Okay. Yeah, no, it's like I mentioned, nobody cares about cadmium. Okay, so, yeah, so since we don't use Roman numerals, we know that zinc is +2, and we know that 2 chlorines of each of -1 have to cancel out with the 2+. And an iron 3 oxide, Fe3, these are the toughest ones. Fe3 means it's +3. Oxygen we know is 2-. How many Fe3s will bond to the O2 minuses? So we gotta see, it's 3 and 2. It's a little bit more difficult. So if we do the least common multiple of 3 and 2, meaning multiplying them together, you get 6. You end up with 3 times 2 for here. Oxygen 2-. If you have 3 of them, 3 times -2, you have -6. If you have 2 Fe3 pluses, you have +6. And then they both cancel out to 0. But the key thing here, the formula for iron 3 oxide is not Fe3O something. It's Fe2O3. That's where people get confused, because this Roman numeral is not the number of metal atoms. It is the charge of each one of them. So if you see that the charge of oxygens, all of them combined, is -6, because it's 3 times -2. That means we need to distribute a +6 charge into 2 iron atoms, Fe2, meaning each one will have +3. And that works out perfectly. Okay, polyatomic ions. So what this means, if you break down the word, polyatomic, meaning poly, more than one, atoms, atomic, right? So that means that you have more than one atom, ions. That's exactly what it is. They are groups of atoms with an overall charge. So you can view them as literally that. View them as singular elements, even though they're composed of many elements. And you just think, all right, that whole charge packet, that whole packet of elements, that compound, is a charge by itself. It has a charge by itself. Excuse me. So here's how that works. So sulfate is one of them. You've probably heard of some of these. Ammonium, nitrate, right? Sulfate. Those are some common ones, where sulfate SO4, this entire SO4 has a 2- charge. The NH4 has a +1 charge. The nitrate NO3- has a -1 charge. Those are some examples. Now here is a list of common ones, but you will not need to know any of them. You do not need to memorize them. Well, honestly, you can look them up, because let's not beat around the bush. You're going to be taking an exam on a computer. I've done that before. I know what's going to happen. So you will have the information saying that, CO3 2- is called carbonate, if you ever see it on your exam. So you'll have that information there. So don't worry about that. All right. And some of them, we're not going to go over this. There's some patterns with them, but you can look at this on your own. Yeah, that's just going over them. Chlorine is a weird one. Chlorine is like 4 levels of chlorines. So ClO is hypochlorite. Add another oxygen, chlorite. Add another oxygen, chlorate. Add another oxygen, perchlorate. So it's like a hierarchy of oxygen adding. But they all have the same charge of -1. Why? Because covalent. So why? Because covalent. That makes sense. But realistically, these packets, ClO4, they are bound together covalently. Even though they create an ion by themselves, the individual bonding of chlorine to each oxygen is a covalent bond. And these covalent bonds have a charge, or when it's all said and done, they have a charge. And it happens to be all -1. Okay, so, my bad. I hit the mic. All right, so writing the names of the formulas with polyatomic ions. is actually easier than writing the normal formulas. So all you do is write the metal first, in this case magnesium. Then you write the name of the polyatomic ion. That's it. Nitrate, NO3. But the same mathematical rules apply because you need to determine what is the correct number of either cations or anions that will make the positive and negative charges cancel out to 0. In this case, since nitrate is -1, you need 2 of them to cancel out with a +2 magnesium, making it MgNO3, 2 magnesium nitrate. And you notice how there are parentheses around the polyatomic ion. That is because if you didn't have them, you'll have NO32. That's not correct. But what we want is NO3. The entire packet of NO3 has 2 of them. Very similar to math. We're multiplying it by 2. But we don't put the 2 in the front. We put the 2 in the back. Okay, moving on. So write the formula for aluminum bicarbonate. And if I tell you on your exam that bicarbonate is HCO3 minus, aluminum is Al3 plus, what would you do? You can pause it here, but we're going to keep going. So bicarbonate ion is -1, aluminum is +3. So how many bicarbonate ions would you need to cancel out with a 1 aluminum? And the answer is 3. So 3 of them work like that. 3 minus, 3 plus, 0. All right, good. Sodium phosphate. PO4 is -3. Sodium is +1. Opposite. Meaning opposite as the other example. Now you need 3 of the cations, Na, Na, and Na, to cancel out with 1 of the anions, which is polyatomic, and it is phosphate. So 3 plus and then 3 minus equals 0. Okay, so then you can combine these rules. So you can so if you have iron phosphate, that's not a thing. You need to have iron 3 phosphate, iron 2 phosphate is also a thing. So these rules can all work together. And there is some naming practice, some non-graded practice that I put on Blackboard, and I'll show you after the lecture. And also there's videos at the end. So here are just some examples of ionics. You could do these on your own. I don't want to be redundant. I want it to be a shorter, so you don't have to, I know it's tough to listen when you have other distractions in your home, but you could do these on your own. And then here is a flow chart. I don't like this flow chart. So all we went over so far was this half, ionic. So that's ionic, metal, and nonmetal. Key thing to remember, ionic, metal, nonmetal. That's how you determine, that's the first question you should ask yourself, is what is it, ionic or covalent? They call it molecular. It's the same as covalent. I don't like the word molecular because technically all these bonds are molecular. But they call it molecular. That's an old way of calling it, but we call it covalent, 2 nonmetals. All right, so you can, this is more practice, name them. All right, more practice here, name them. More practice here, name them. All right, so now let's get to the molecular or the covalent bonds. And these are very easy. They're easier. And you could pause it here if you need a break. Pause it wherever you want, and you can slow it down, do whatever. All right, so the covalent bonds, they are 2 or more nonmetals that share electrons with each other to make these bonds. And they want to share enough valence electrons so that they have 8 each. And they use these prefixes. So think of, always go by an example, something that you know in everyday life. You know 2 things already that are common covalents: carbon dioxide, carbon monoxide. Those are great examples. They are just 1 oxygen off from one another, but carbon dioxide, you need to live, and carbon dioxide, you need to live. Carbon monoxide will kill you. So that prefix makes a big difference when you're talking about that. If you left it out, somebody wouldn't know what you're talking about, and that's really important to know in that case. Now, these are where the prefixes come from, and I would expect you to know all of them, but they're not too hard. 1 through 4 may be a little bit different than you're used to. Mono, di, tri, tetra. 4 is tough. People put like quad and stuff, but it's not. It's tetra, like Tetris. And then after 4, it's just very simply the shapes: pentagon, hexagon, heptagon, octagon, nonagon, decagon. So those 5 and up should be pretty easy to know, but the 1 through 4 you should study. So the way you name them, and this is The rules are written right here, but let's just go here. Whatever. The rules are written there. You could have read it. But basically, let's learn from example. What you're doing, carbon dioxide. You write the first element, carbon. Then you write no matter how many of the second element there are, you write the prefix for it. Oh, CO2, meaning there's 2 oxygens, dioxide. And you always put the IDE ending. That's common in both ionic and covalent. Carbon, oxygen, 1 oxygen. Carbon monoxide, not monooxide. It's just, you make them flow to monoxide. It could get weird. For example, mononitrogen, mononitride, that's a thing. So you could have carbon mononitride. In other words, it's called cyanide, but you can call it that as well. Anyway, so something that's a little nuanced. So like, here's the vowel rules here, but just make it flow. That's my rule. So there's another rule. If you had 2 carbons here, right, for carbon dioxide, let's say you had C2O2. It wouldn't be carbon dioxide anymore. It would be dicarbon dioxide. In other words, it's a little tiny trick or rule. If the first, and this is important to write down, if the first element in a covalent bond is only 1, you do not write the prefix. So you can rewind that, or I'll say this second rephrasing of the rule. If your first element is more than 1, you always write the prefix. If it's 1, no prefix. There's no monocarbon dioxide. There's no monocarbon monoxide. There's just carbon dioxide, carbon monoxide. So that's how that works. Okay, so here's some examples. You see how every single one where there's only 1 of the first element, carbon disulfide, carbon dioxide, nitrogen oxide. That should be nitrogen monoxide. But sometimes when you look online, there will be what we call trade names. So what that means is in chemical factories and whatever, they don't like to write out the perfect official international naming, which is what we're learning. They don't like to write that all the time. So they write a shorthand version. So nitrogen oxide, if you say that in a chemical industry, you mean NO. So, but this should be, I don't like that it says it here, it should be nitrogen monoxide for learning it from the chemical standard. This should be dinitrogen monoxide, sulfur dioxide, sulfur trioxide, sulfur hexafluoride, for example. Okay, moving on. All right, so name this one. And so it's pretty easy when you get to it. You can pause it here, but we're just going to keep going. So it would be, since there's only 1 of the first element, you just name it, nitrogen. Then there's 3 chlorines, chloride, trichloride. So the answer, nitrogen trichloride. Easy. All right, let's do it again. So this case, there's more than 1 of boron. So you're actually going to put diboron trioxide would be your answer. Diboron trioxide. And I think this is a tough one because if you look on Google, and I stumped a lot of people with my homework for this a while ago, I think in another class. I put this as an example, and you Google this, you get boron trioxide. You don't get diboron. And when people would put boron trioxide, I would know they looked at Google for the answer. So I'm tricky like that. So you just know the rules. Okay, moving on. So we can go backwards, and it's pretty easy. It's easier to go backwards. So name the molecular formula for diphosphorus pentoxide. Diphosphorus, 2 phosphoruses, pentoxide, 5 oxygens. And that's exactly what it is. P2O5. All right, we know that already. Here's the list again. That's basically it. So here's that's basically it for naming. There's a little bit extra. So here is some questions. Go through it. Here's the answers for them. Cool. You can pause it here. All right, good. And remember, to tell if it's ionic, always ask yourself, is it a metal or a non-metal? In that case, ionic. Or is it 2 nonmetals? In that case, covalent. But there's one little tiny exception. If you have ammonium, which is NH4+, right here. Ammonium, excuse me. I don't have coronavirus. If you have ammonium, which is NH4+, that is the only cation that does not have a metal in it, right? Because it has NH and an H. They're nonmetals. But when they bond together, they make a positive charge. So therefore, it can be a cation. So ammonium phosphite is what this is. And it's still considered ionic because whenever you have polyatomic ions, you just assume it's ionic. That's a really good rule to know. If you're confused and you see me give you a hint about what type of ion it is, polyatomic ion, you automatically know it's ionic. So that's a good little hint. All right, and this is slide, let me just check. This is slide 97, right? Yeah, 97. And this slide tells you the rules, like Fairly Odd Parents. If you like that show growing up, I do a lot. So here's basically my interpretation of the naming rules and what you should know for charges. You see how covalent is a lot shorter, right? Because it's easier. So you can take a look at that, study from this slide first, I would suggest. And then, we're going to do Lewis structures. Okay, so Lewis structures aren't too bad, and I may give you 1 or 2 questions on it. But basically, they are the way of representing two-dimensionally the covalent bonds. So ionic bonds do not have kind of a geometry, meaning it's one ball attached to another. There's no orientation of one atom to another. It's just attached. In covalent, you have different types of orientations, meaning in this case, CH4, you have hydrogen here, hydrogen here, hydrogen here, hydrogen here. In ionic, if you had 4 hydrogens, it would just be 4 different balls always moving, right? So basically, we're going to go to a tougher example. So there's a video on this. I would suggest watch the video because they actually write it out. I'm going to get some kind of way to write it out and to show it on the screen, but I'm not there yet. Technically, we shouldn't even have class today, but whatever. We want to get ahead. All right, so the Lewis structure, basically what it is, and here's the steps on how to do it. You write out your formula. Let's say if you want to figure out the Lewis structure of NH3. You assume that hydrogen is never in the middle. That's a common question is, how do I write these Lewis structures if I don't know what's in the middle or how it's oriented? If you ever see one element and then more than one element, usually the one element is in the middle. So, and you'll see how this makes sense. If you do it the other way, it won't make sense. Now, nitrogen's in the middle. You're going to write nitrogen, N. And then hydrogen is going to be one here, one here, one here, before the dots, before the lines and the dots. Then you are going to draw the dots that represent the number of valence electrons around each atom. Meaning, nitrogen, if you look at the periodic table, has 5 valence electrons. So you're going to write 5 dots. 1, 2, there'll be 3, 4, and 5. Then, on hydrogen, you're going to write 1 dot, because hydrogen is in group 1A, only 1 valence. 1, 2, 3. Then, you will, knowing the octet rule, you will try to make covalent bonds that make sense. Meaning, for hydrogen, does not meet the octet rule. Meaning, it only has 1 possible bond. And it only wants a maximum of 2 electrons. So, nitrogen, though, has 5 valence electrons. It wants to bond with 3 different things. 5 plus 3 is 8. In other words, the number of valence electrons plus whatever it takes to get to 8 is how many bonds it needs. Halogens, 7A. 7 valence electrons plus 1 bond equal 8. That's how many bonds it needs. Nitrogen has 3 bonds that it needs. Therefore, there's 3 bonds here. And then, if you look at the octet rule, hydrogen is happy, meaning it's 2 valence electrons, 1, 2. And each of these bonds, this line represents the bond. So, I think I'm going to have a separate video on this because this is a terrible explanation because I can't draw it. But just try to bear with me. So, here we go. So there it is. So if you count up all the electrons in nitrogen, you have 1, 2, 3, 4, 5, 6, 7, 8. Each line counts as 2. So here, in this bullet point, the shared electrons or bonding pairs are shown as 2 dots or a single line between atoms. So each single line represents a covalent bond where 2 electrons are shared. So nitrogen has 8. 1, 2, 3, 4, 5, 6, 7, 8. Hydrogen has 1, 2, 1, 2, and 1, 2. So everything is happy. Okay, and here's how it can work here with difluorine. In other words, fluorine gas, F2. So F2, you have 2 fluorines, right? 7A, meaning has 7 valence, needs 1 more. And then it meets another fluorine. Hey, I need 1 more. Oh, me too. Let's share. That's exactly what they do. They have 1 pair of bonding, and it creates a covalent bond like this, and you get the molecule. That's how it works. Okay, so here's, like I was saying before, the bonding patterns of some elements. And there's 2 main ones that do not follow the rules. So the rule I said before was that you take the number of valence electrons, whatever it takes to get to 8, that's how many bonds it needs. 7A has 7. It needs 1 more to get to 8. That's why fluorine, chlorine, bromine, iodine need 1 more bond. They need 1 bond they do 1 covalent bond. 6A, they need 2 more to get to 8. So 2 bonds. 5A, 3 more. 4A, 4 more. 3A should be 5 more, but boron is a little bit complicated. Boron does not form the octet. It likes to have 3 bonds. For boron, you could think 3A, 3 bonds. But it doesn't work that way for everything else. I mean, I guess 4A could be 4 bonds, but it doesn't. That's not the trend. 5A is 3 bonds, 6A is 2 bonds, 7A is 1 bond. And then 1A is also 1 bond. So I guess you could think this half of the chart is the number of bonds, 1, 3, and 4. The other half is 8 minus that. 8 minus 5 is 3. 8 minus 6 is 2. 8 minus 7 is 1. But however you want to think about it. Okay, so here is what I was trying to explain before about how to draw the Lewis structures. So you write the each atom first, and then you write the electron dots around it, and then you connect the dots, basically. So here are some formulas. We went over NH3 already, and notice that in some of them there are electrons. They're not paired with anything. They're not there's a lone electron pair, meaning they're not bonded with anything. And that's possible as well. In water, there's actually 2 of those. That's what makes water very polar, meaning it likes to react aqueously, and we'll talk about what that means. Okay, so you can draw the Lewis structure for PCl3 whenever at your leisure, and you put phosphorus is in the middle. You assume it's in the middle because there's less of them, and there's 3 chlorines. They go around it, and then you should write the dots. Wait a minute. You write the dots. So 5 dots around phosphorus, 7 dots around each chlorine. See, each one has 7, and then you can add those up for a total of 26 dots. But that could be a separate question. And then you write the bonding pairs, and then technically here's what it's going to look like at the end. So it would look like that. Okay. There are also double and triple bonds, meaning you don't only share 1 pair of electrons, you could share 2 pairs of electrons between atoms. That could happen. And even 3 pairs. So that you'll see how that works out. If you try to draw the O2 molecule, for example, you'll have 1 oxygen will have 6, the other oxygen will also have 6, and then they will each want 2 from each other, so they will share those 2, and then you get a double bond. Okay, the last thing we're going to cover is electronegativity. Now, we're going to just cover the trend and what it means. So electronegativity is the atom's ability to attract a shared pair of electrons in a bond. In other words, it's very similar to electron affinity, meaning how much does an atom want an electron? That's basically what it means. In layman's terms, it's how much an atom wants electrons. So the trend is important. We're not going to go over numbers, we're going to go over trend. The trend, the electronegativity increases as you go from the bottom left to the top right. Fluorine has the highest electronegativity, meaning out of all the elements, it wants electrons the most. Why? Because it is 7A, it really wants that 1 electron, and also it's pretty small too. So it really has the nucleus with the positively charged center is kind of exposed in comparison to every other larger element. So it is the perfect storm of wanting that 1 more electron, and it's pretty small, so that there's not much what we call electron shielding of the nucleus, meaning there aren't inner shells of electrons shielding that nucleus away from the positive charge, or shielding the outer electrons away from positive charge. So it's a very superficial nucleus in that case. It's very close to the surface, close to the valence electrons in comparison to the other ones. And you can see how it decreases. The metals have very low electronegativity. Why? Think about that. You can pause it and think about why. But the reason why is because metals, they don't want to gain electrons at all. They want to lose electrons. So why would they want a capacity or a big number to gain electrons? They don't want that at all. They want very small. But you see the nonmetals have the highest electronegativity in general. The metalloids are kind of in the middle, as you could expect, right, by definition. But a good question that someone in my Tuesday class asked is that, what kind of bonds do metalloids do? And the answer is mostly covalent. But it could be either or, like boron, silicon, tellurium. Really, I think anything on the right side here is more likely to be in a covalent bond. But don't quote me on that. So mostly covalent. Okay. So if you have, knowing this electronegativity, if you have two atoms that are covalently bound, that have a different level of electronegativity, this is what we call polar. So water is very polar because oxygen, if you go back, oxygen is 3.5, pretty high electronegativity. It's second only to fluorine. Hydrogen, which is also in water, has 2.1, very small. I think it's the smallest out of all the nonmetals, and tied with phosphorus. Now, if they bond together, there is going to be a greater pull of the electrons. Remember, this electronegativity number represents the pull of the electrons. Greater pull in the direction of the oxygen. So we call that a partial charge, partial positive or partial negative charge that is formed even in a covalent bond. So to reiterate, in ionic bonds we talked about charges. In covalent bonds, if they're polar, we can also have charges. But they're called partial charges. They're not as strong as ionic charges, and they only occur by a unequal sharing of electrons. So you can think about every covalent bond as a tug of war between electrons. Hydrogen versus hydrogen in this case. The tug of war will be pretty equal. They're equal. Hydrogen versus chlorine. Chlorine is much more electronegative if we go to the chart. 3.0 versus 2.1 is much more electronegative than hydrogen. Therefore, the tug of war, chlorine is stronger and will win. Therefore, it will gain a partial negative charge, meaning those electrons that it brought closer to its nucleus are now giving the chlorine a partial charge. And then and vice versa, the hydrogen will have its electrons further away. Those bonding electrons will be further away, making hydrogen have a positive charge. Don't worry about electronegativity differences. If they're different atoms, they're probably polar. I don't even trust these numbers, because even chlorine and bromine, they have a very small electronegativity difference. We in the science community still consider it polar, weakly polar, but it's polar. So don't go nonpolar. It's if they're zero, if they're the same atom. Nitrogen, they're completely nonpolar. Oxygen gas, hydrogen gas, fluorine gas, very nonpolar. And here's some that are polar, which are higher electronegativity differences. But don't worry about numbers. I'm just going on trends. So what I'll ask you on the exam is, what has a higher electronegativity? Fluorine or phosphorus? And your answer would be fluorine because of the trend. If I ask you, is the chlorine phosphorus bond polar or nonpolar or ionic? What would you say? Oh, they're two nonmetals, so it's definitely not ionic. Their electronegativity is based on the trend. Chlorine is higher because it's more to the right. Therefore, it's probably polar. And that's right. So I would answer that as polar covalent. Okay. So these polar covalents, they form this dipole, what we call. A dipole meaning two poles. So basically we draw an arrow. I'm not going to ask you to do this, but in order to understand the notation is that the arrow is facing in the way that the electrons would go. In other words, it's facing the most electronegative atom in each bond. So in this case, carbon and oxygen, oxygen's more electronegative. Therefore, the electrons would go in the direction of oxygen in the bond. They will be unequally shared. So they'd be like kind of like here, as opposed to in the middle. And then that same thing goes for all these other ones. Okay, now, an ionic bond. Scratch this. I don't care about this chart because you should not look at electronegativity to tell you if it's ionic, because you should look at what type of elements we're talking about. If you have metal, nonmetal, automatically ionic. Don't need to look at electronegativity differences at all. So I don't even like to, it's confusing that they show this. But generally, if you want to compare, they have the biggest difference. But again, metal, nonmetal, automatically ionic. Okay, don't worry about the numbers. Don't worry. Yeah, this is just a chart summing it up. Just examples. You could do this on your own. So basically, categorizing these bonds. So let's do it now. Kn. K is a metal, right? Automatically ionic. Boom. No. Oh, they're both nonmetals. That means they're covalent. Either nonpolar covalent or polar covalent. They're different. Oxygen is much more electronegative. Polar covalent. These are the same. They're nonmetals. Chlorine, chlorine. Nonpolar covalent. HCl. We went over that example before. Cl, much more electronegative. Polar covalent. So there are 3 types of bonds that we learned today. We learned all about them. Nonpolar covalent, where they're basically the same atom in the same nonmetal. Polar covalent, where they're different nonmetals. And ionic, where they're metal and nonmetal. So here's our answers. Okay. So that's everything. Here's some stuff. So naming ionics, video. Naming covalents, video. Electronegativity and bonding, bond polarity, video. Now, what I'm going to do is, so I'm going to send an announcement after I post this, because I can't really think straight right now. But what we're going to do is, under assignments, I have all this stuff. Maybe you've seen this before. I have, where is it? Naming compounds practice, non-graded. Definitely look at this file right here. Yeah, in-class worksheets, we don't have one until chapter 8, because we don't, I might add more, but I'll let you know. And then homework, chapter 6 homework for my Tuesday class is due tomorrow. I mean, today is, I'm going to post this on 3/16, that's Monday. It's going to be due tomorrow by midnight, 3/17, under chapter 6 homework file submission. And it'll be out of 10 points, and I will have them graded fast, because I have nothing else to do. Now my Friday class, I'll go to that section, 144. Oh, wait, I think I was just there. But anyway, Friday class, same thing, but it won't be due tomorrow. It'll be due on Friday, which is the 20th. So Friday the 20th at midnight, it'll be due right here. And if you have a problem submitting it, you could just email it to me. But I'd rather not get 100 emails. So, and I had to look through everybody's homework and download it and all that stuff. So if you can try to get it to work through Blackboard, I'd really appreciate it. Okay, so that's it. And if you have, just under an hour, nice. So if you have any feedback, I really suggest feedback. I know this wasn't the best because I still need to like get some way to write stuff. Oh, open the wrong thing. So I need to get some way to write stuff and like talk to you at the same time. Maybe I'm pretty sure my audio quality is pretty good, but it might not be loud enough. So let me know if there's any problems. All right, that's it. If you have any questions, let me know. Email me, and I'll put the forum up for both classes right now. All right, good luck, and stay safe. Don't get coronavirus. Wash your hands. And honestly, if you're in the city, stay inside. That's the best thing right now. So, all right, until next time, bye-bye.